Hello everyone to the second part of the lesson today. I hope you've had a chance to watch the first one so that you have some ideas about what it looks like to try and graph in 3 dimensions, so that when you see something like this here, this is not a surprise as to what the three axes look like. What I want to do now is take that idea and just look at how we would represent some vectors and work with vectors in this three-dimensional space. So in 3 dimensions, we also call this then 3 space. Or we call this r cubed, our real numbers cubed, representing our 3 different directions. And like 2-dimensional vectors, we're going to represent these vectors in 3 dimensions using two methods, either using our components, okay, or using our standard basis vectors. So for example, if I wrote this as a component vector, we would use this idea of an ordered triple. If I had, say, vector u, which I could write as a position vector OP from the origin to some point P. And let's say, for example, we had components then 4, 3, 5. Likewise, we could use our standard basis vectors, but we first need to extend that definition from 2 dimensions. We still have this vector I, which is a unit vector in the x direction. However, now I need an ordered triple. So I is 1, 0, 0. That is then coming 1 unit out in our x direction. I would have still vector j, which we then describe as 0, 1, 0. In other words, 1 unit out in our y direction. And we define a new one in alphabetical order, I, j, and k, which is now 1 unit out in our z direction, so moving 1 unit up. So I could take this same vector u, or vector OP, and I could now write this using these standard basis vectors the same way we did in 2 dimensions. In other words, if I'm moving 4 units in x direction, I would need 4 of these, so I had to have 4i. If I'm moving 3 units in the y direction, then I would need 3 j's, and if I'm moving 5 units in the z direction, then I would need 5 k's. So using our standard basis vectors, we can write this in the same way that we did in 2 dimensions. We just have this added piece on the end. Again, if you've watched the video on graphing 3 dimensions, this shouldn't be a surprise. If we want to try to draw a picture of this, then I'm going to come 4 units in the x direction, 1, 2, 3, 4. I'm going to go 3 units in the y direction, so 1, 2, 3. To try and locate that, I'm going to put these two things together. So we start drawing some lines that are parallel to the axes. So there's that spot that is 4 out, 3 to the right. I'm now trying to come 5 up. So to do that, 1, 2, 3, 4, 5. There is now 5 up. Again, like we did in the last video, I'm going to create that rectangular prism. And it's that rectangular prism that's going to then locate that last point. So as I do that, again, parallel to the axes, I end up with something like this here. So we continue to draw in that rectangular prism just very lightly. Okay, there it is. There is that point P. So if I want to now try and draw that vector, it's going to look very small, but it's actually coming out towards you in 3 dimensions. There is that vector u, or that vector OP. Again, the idea is that I have this point here, which would have the coordinates 4, 3, 5. Remember that these are called coordinates when I draw this as a point. But as a vector, I could also then write this as 4, 3, 5, and that these would now be its components of the vector. A slight different, a component is a direction, how you're moving from the start to the end, whereas this is just this point here. So it's the same definition, but now trying to do that same idea in 3 dimensions. And that's why we use these vectors, because they very easily translate from 2 dimensions to 3 dimensions. And eventually, if you wanted to, you would have this abstract concept where you could actually have a 4th and a 5th and a 6th dimension. You wouldn't be able to picture it visually, but you could then do all the same algebraic operations that we're going to learn with higher dimension vectors as well. The only real question I want to look at then is how would we find the magnitude of this vector? This looks very short, but it's tough because in 3 dimensions, this is actually out 4, right 3, up 5. So this is a lot longer than what it looks like when we see this in its 2-dimensional version here on flat on this page here. What I like to do is, if this is given to me in its basis vector form, I really prefer the component vector form, so I usually just switch this over and say this is the same as 3, negative 4, 6 as a component vector. If I want to try and draw this, like in our last video, because I am going to use a negative y value, I have extended the y-axis in the negative direction here. So now if I try and draw this vector, we are going to come out 3 spaces. So 1, 2, 3, there is out 3. We want to go to the left 4, 1, 2, 3, 4, there is negative 4. Again, I always like to stop at this point for just a second, start drawing this first part. Here, there is the start of that rectangular prism. We need to go up 6 spaces, so 1, 2, 3, 4, 5, 6. So if I now continue to draw, there is up 6, or we can also do this way here. There is our up 6. Again, if you want, use a ruler. If you want to try to make sure that these all look like they are exactly parallel as you draw that rectangular prism. I'm just kind of freehanding mine here. Okay, that's how comfortable you feel with doing it. There is the end of the vector. So if I try to draw now vector u, I'm moving from here to here. There is that vector u. And now that we have that vector, what I'd like to try and do is figure out how long is that vector. And really what we're going to do to get magnitude is sort of an extension here on Pythagorean theorem. If I want the length of this here, I could actually draw a right triangle here. I could draw a right triangle that comes down that side and goes back to the origin. So again, in 3 dimensions, you would need to try and picture this here as being a right triangle. I know how big that side is there. Okay, this is 6, this is 6 units long, but I don't know how long that side is. But if you look on the bottom, we also have a right triangle. So I could figure out how big that side is by using these dimensions here. So if I want that side there, okay, I could use Pythagorean theorem down here, and I would be able to figure out that that side is actually the square root of 4 squared plus 3 squared. Okay, a squared plus b squared is c squared, and take the square root. So there is the length of that side. And that actually works out to a nice number. I'm going to leave it like that, but that would actually work out to a nice number for us. So we could actually get that length, and now if I know that length, I could square this in Pythagorean theorem, square this, and add this, take the square root. That would give us this side here using Pythagorean theorem. So what we end up with here is then that the magnitude of u squared is equal to, from Pythagorean theorem, the square root of, I want this squared and this squared. So I'm going to go now back to my original dimensions and say, well, this is 3 squared plus negative 4 squared, okay, as a dimension here. So I'm going to put the negative in, and I would take the square root of that. That gives me that. Square it, gets rid of the square root. So now it's that dimension, and I'm going to now add on here that we have 6 squared. So these two here are calculating this length, okay, and then do Pythagorean theorem again, and we end up with this formula here. In the end, we end up with this extended version of Pythagorean theorem where it looks the same, except for we just have a 3rd dimension as we do this. And if you put this into your calculator, what you will find out is that this actually works out then to the square root of 61. To figure out a direction in 3 dimensions, that's a little bit trickier. If you want, you can read in a textbook. They do talk a little bit about direction cosines. I'm not going to worry about that too much because we don't really use it a whole lot in this course. But there is an idea where you can figure out some angles. You're going to calculate the angle of this vector to each of these axes, and they're called direction cosines. So if you want to read about that in the textbook, you can. I'm going to stop there for today. We've looked at how we can plot vectors in 3 dimensions and how we can figure out the length of that vector. In general, then, if I am given any vector that is in 3 dimensions and I want its magnitude, we can say then the magnitude of u is really just equal to the square root of a squared plus b squared plus c squared. So it's really, there's 2 dimensions, and we're just extending on Pythagorean theorem for 3 dimensions. Have a good day.